All right, so we're going to do some acid-base notes today, and just kind of start with some items that are pretty standard stuff, things that could show up on the test, and nothing real specific, because we're not going to have a lot of time to get into the specifics, but just kind of an overview. So first of all, let's draw out an acid. So let's go ahead and draw out an acid. So this is H2SO4. This is sulfuric acid, one of the most common acids in the world in terms of industrial acids, like things that we make. And then let's go ahead and put a base on here. So let's just put sodium hydroxide. Okay, so main thing is that with an acid, with a base, there's a couple of ways to look at the definition. So this first one I think is going to be a little more common in terms of what we're going to talk about in class, the Arrhenius definition. And so what the Arrhenius definition says is that it's really based on a part. So if you look here at the front of an acid, we're always going to have a hydrogen, at least in the non-organic acids. So that's the ones you're going to see. So you're going to have a hydrogen in front. And then over here in the base, you're going to have this OH or hydroxide. So these are going to be the pieces that are going to be identifying our acid or our base with one of the definitions. And so if we go down here, the Arrhenius definition is going to say that an acid is going to break apart to make hydrogen ions. And so the fancy word for that is dissociate. But we're just going to say, I'm just going to sneak this in here. We're going to say it's going to break apart to form. And what it's forming is hydrogen ions. So H+, that is a hydrogen ion. Okay, it's going to break apart to form the hydrogen ion, where the base is going to do the same thing. It's going to dissociate or break apart. Dissociate's the fancy word that means it comes apart in water. But for you guys, break apart is probably the best way to do it. So break apart to form, and then instead of a hydrogen ion, we're going to make the hydroxide ion, so OH minus. So the thing that makes the acid, the things that makes the base, the thing that makes them do the things they do is this component. So sulfuric acid, all of its properties based upon that hydrogen component, and the same with the hydroxide in the base. And so bases are going to make this, acids are going to make that. And so that kind of gives you a kind of a fundamental definition of those two. Now, I think that's pretty easy to spot that on a test. So on a test, let's just get a quick question. I say, okay, you got KOH, you got HCl. Which one is the acid? Well, it's this one because it starts with a hydrogen. Or which one's the base? Well, it's this one because it ends with OH. So I think that's a pretty straightforward way to look at it. Okay, I don't think the Bronsted-Lowry definition is going to come up a lot in our class because we're not going to have a lot of time to get into some of the specifics. But what it says is that the hydrogens are basically going to be the thing we're talking about. So the acids are going to give away hydrogens, and the bases are going to accept them. And so we say that the Bronsted-Lowry is going to donate. Get a pen color here. Says that they're going to donate. Same thing, H+, where the base is going to accept. So basically, the idea is that the hydrogen goes from one chemical to another, but we're only talking about the hydrogen ions. And so where this is different is that we don't care about OH. This is less likely to come up than the Arrhenius, because this is a much closer to what we've talked about in class. We talked about, hey, acids start with H, and bases, this new thing is that they have the OH at the end. So I would focus in on that. All right, Let's talk about the taste and some of the properties that are very easy to spot. So think about acid, think about citrus fruits, vinegar, things that we actually use as in food products. The key idea there and the key thing that's going to come up is going to be the taste. And so the acids are going to have a sour taste. So if you think about the sour candies that you like, if you think about things like lemons, limes, then that sour component could be based upon like a citric acid component, or in a vinegar, maybe a sour component in a sauce, things like that. So a pickling, and so that sour is part of the acid. Now the bases are not things that we normally eat. These are not things that we normally ingest, and they have a bitter flavor. They taste terrible. So if you ever watched that Christmas movie called The Christmas Story, where Ralphie is using profanity, and so his mom sticks the bar of soap in his mouth, that's because it is going to taste bitter and terrible, and so that's what's going on. Bitter foods are not necessarily things that people like, and so you don't see a lot of bitter foods, but that bitter flavor is due to a basic component, a base component in the food, or the bar of soap, as you will. Now, feel. How do they feel? Okay, so we're not talking about like, oh, they're burning up my skin. We're talking about like you come into contact with them. What would they feel like before there was a reaction? So yes, the acid could be damaging to your tissues, and so could the base. But what would that feel like if you got one on your skin? And so the thing with an acid is it doesn't really feel any different than water. And so the feel is going to be like water. It's not going to have a specific feel to it because it is just like water. And now it could react at some point, depending on how strong it is, but initially it would just feel like water. Now the base, though, is going to have a slippery feel, all right? A slippery feel. So we can kind of go back to the idea here of Ralphie and the soap in his mouth for using the profanity when he was helping his dad change the tire. That slippery thing, again, is the bitter taste, the slippery feel. These are things that with soap, you've used soap in your life, and so you would know that if you don't wash the soap off, it's going to have a slippery feel to it on your skin. Bleach is the same way. You get bleach on your hands, it's going to feel slippery. It feels like there's something you need to wash off of your hands. Part of the way soap is useful is it's helping you move your hands around, create that mechanical action that's getting rid of germs and things like that on your hands, and part of that's because you don't want a slippery hand when you're done. You want to get that soap off of there. So that's just a trait of the bases. Now, reactions with metals. This is not going to come up a lot, but some metals are going to react with acids to form hydrogen, and so some will react and form hydrogen. Now, that is a problem because if you're putting acid in contact with metal, and so we don't have a lot of this anymore, but if you have metal pipes in your home, and a lot of older houses and still have metal pipes, then that acid going into the pipes could be a problem. So that's why you're not putting acid into pipes, into sanitation, into sewage, into things like that, because it can react with the metal in the pipes. Now, a base, on the other hand, is not going to have a reaction, and so this is no reaction. So a drain cleaner is a base. So if you look at a drain cleaner, Liquid Plumr or something like that, it's going to have a component like KOH or NaOH. It is still very damaging to organic tissues, so grease and hair and things like that, but it is a base, and so it's not going to have any effect on pipes. And so that's why bases are what they put into drains to do the chemical drain cleaning. So, okay, conducting electricity. So that's what this is talking about over here. What do they do in terms of, do they conduct electricity? And so when you think about conducting electricity, what you need to conduct electricity is you need different charges. And so what happens is if you have charges like these things, if you have things like this, or things like this, you have charges in solution. If you have charges in solution, then the solution can conduct electricity. So we talked about at the very beginning, what do acids do? They break apart to form hydrogen. What do bases do? They break apart to form OH. They do this in water. And so both an acid and a base are going to be able to conduct electricity. So what that means is that this is not a good way to determine if you have an acid or a base. And so do they conduct electricity? Yes, for acids, and yes, for a base. And so this is not a particularly great way to determine if you have an acid or a base. Things like the taste, although again, we're not tasting things normally in the chemistry class, but with a food product you could. Or if you look at the actual chemical makeup, breaking up into hydrogen, feel, things like that. All right, so I'm going to slide down here, and we got acid-base indicators, and we got the term amphoteric. Okay, let's talk about acid-base indicators. Acid-base indicators are things that change color to determine, well, not really to determine pH, but they change color with pH. And so you can use a pH key like we have done in some of our labs to determine what you have. And so an acid-base indicator is going to change color with pH. Now, that can be problematic if it doesn't have a lot of different colors. So some acid-base indicators are very specific and they only have a small range. Some of them have a broad range, like a universal indicator that can do tons of pHs. And so it just depends on your indicator as to what pHs it's going to give you. All right. And again, this is things like universal indicator, the cabbage juice, the litmus paper, phenolphthalein. There's just tons of them. So amphoteric. This is simply something that can be an acid or a base. So it can be classified as both. And so you can consider it depending on the situation. So this can be considered an acid or a base. And so water is something that is going to have properties that are like an acid sometimes, and sometimes they are like a base. And so water is often considered amphoteric, meaning it can act like an acid or it can act like a base. Things that are kind of hovering in the middle, in the neutral area, a lot of times are going to do that. Okay, this is just a simple picture of an indicator. So this is just a litmus indicator, so litmus paper. Litmus paper basically has two options. It says, hey, you got an acid, or hey, you have a base. It doesn't give you pH, it just is a yes or a no. So this picture is not the greatest, but litmus paper is often pink or purple. And so you have this sort of pink or purple section here, and that's the way the litmus paper starts off. It starts off pink or purple. And then when you put it into an acid or a base, if you put it into a base, then this part of the paper that gets wet with the base is going to turn blue. So I always think of litmus paper as blue for base. And then if you put it in an acid, then the paper would turn red. And so you only get one of these. So it's not going to do both things. It's like either going to be red for an acid or blue for a base, but not both. So just kind of remember blue for base for litmus paper. So I'm going to pause it because I'm going to run out of time on this section, and then I'll pick up on another section of the video.